everyone. Myself, Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about star to delta and delta to star transformation techniques in case of series and parallel combination of the resistors. So here, actually, why we are going to discuss about these star to delta and delta to star transformation and at what particular situation or when we need to apply these transformation technique. Okay, so this is also a one kind of network reduction technique, and it is used to reduce the complex circuit into a simple circuit, and also it is used to find an equivalent resistance between any of the two terminals, because usually if you want to find the equivalent resistance between any of the two terminals, we usually apply the series and parallel combination of the resistance, which means we will identify what are the two resistors are connected in series, then we will replace the two resistors with the equivalent resistance, and similarly if we find any two or more resistors connected in parallel, then we will replace those resistors with the equivalent resistance. But in some cases, okay, in some complex networks, it is difficult to identify whether the two resistors are in series or parallel, because as we know, according to the conditions, okay, if the two resistors having one common node and the common node should not share with any other node, then only we can say those two resistors are in series, right? But suppose in a network, okay, or in an electrical circuit, any two resistors having one common node, but the common node is connected to some other node, then we cannot define whether those two are in series or parallel. So in that case, okay, we can use this star to delta and delta to star transformation. Okay, so which means more than two elements, okay, in a particular node, at a particular node, more than two elements are connected, then we can apply this star to delta or delta to star transformation. Okay, so this is the representation of the star network, and this is the representation of the delta network. Okay, so which means the three elements, if the three elements meet at a node, then those three elements are said to be a star connection. And where if the three elements form a closed path, then they are said to be a delta connection. So now, in this class, we are going to discuss how we can convert star to delta and delta to star transformation. Which means, suppose here, as you can see, in the first figure, this is a star connection. So in this star connection, we are just transforming this star connection into delta, so that here R1, R2, R3 becomes RA, RB and RC. So which means here RA is connected in between X and Y terminals, but in between X and Y terminals, okay, so the X terminal is connected to R1 and Y terminal is connected to R2. Okay, then what is RA in terms of R1, R2 and R3, and what is RB in terms of R1, R2, R3, and what is RC in terms of R1, R2, R3. Okay, that we are going to find in today's class. So for that, here let us consider a star network which consisting of the resistors of R1, R2 and R3. So now we are transforming the star network into the delta network. So if you want to transform the star network into delta network, okay, you have to join the various terminals, because here, as you can see, in between X and Y, okay, so just join and place one resistor. Then just let us consider this resistor, or the resistor which is connected in between X and Y terminals is RA, and similarly the resistor connected between the X and Z terminal is RB, and similarly the resistor connected in between the Y and Z is RC. Okay, so which means initially there is a star network in a particular circuit. Okay, now because it is difficult to identify whether these two resistors are in series or parallel, any of the combination, as you can see, because if you take R1 and R2, so R1, R2 having only one common node, but the common node is connected to R3 element. So that's why R1, R2 only one common node, because these two doesn't have any two common nodes, so that's why these are not the parallel. And of course one common node, but the common node is connected to R3, so which means these two are even not in series. So we cannot define whether those two are series or parallel. Then how to reduce this network? So in these cases, we are going to use these star to delta transformation. So for that, just let us consider the terminals X, Y and Z. Then join these X and Y terminals, one resistor, and place another resistor in between Y and Z terminals, and place another resistance between the X and Z terminals. So let us consider the resistance between the X and Y terminal which we are connected is RA, and the resistor which is connected in between X and Z is RB, and resistor which is connected in between Y and Z is RC. So now we are going to find RA value, RB value and RC value in terms of R1, R2, R3, which means we are transforming the star network into delta network, which means we are just replacing these R1, R2, R3 in terms of RA, RB, RC, and we are finding the values of RA, RB, RC, okay, by using R1, R2, R3 values, because we know R1, R2, R3 values because our given network is in the star connection. Then we are converting or transforming the star connection to the delta connection. So for the delta connection, we just consider the resistances of RA, RB and RC. So, but we don't know what is RA value, RB value, RC value. But now we need to develop a formula in terms of R1, R2, R3 to find RA, RB and RC values. Okay. Then now let us see how we can find RA, RB, RC values in terms of R1, R2 and R. So here there is a star network and delta network. Okay. So now we are just going to write an equivalent resistance between any two terminals by considering the third terminal is negligible. Okay, which means suppose let us consider the terminals X and Y. Okay, so in between X and Y, how many resistors are there? R1 and R2. But there is a R3 resistor is also connected to this common node. But let us neglect the third resistance when we are finding the resistance between the two terminals. Okay, let us consider. Similarly, here also again in between X and Y. Okay, so how many resistors are there? Of course, these RB and RC resistor is there, and these RB and RC are in series combination. Okay, so which means in between X and Y, the equivalent resistance is RB and plus RC, and the combination of RB plus RC is in parallel with RA. Right. So this way we are going to find the resistance between the two terminals. So first let us consider in the star network. Okay. So at X and Y, what are the two resistors in between X and Y? R1 and R2. So then the equivalent resistance between the X and Y terminals is R1 plus R2, because we are just neglecting the R3 terminal. So that's why here, as you can see, the equivalent resistance between X and Y is R1 plus R2. Similarly, now we are going to find the equivalent resistance between the X and Y terminal. In between X and Y terminal, of course, RA resistor is there, and as well as the series combination of RC and RB is also there. So that's why then the equivalent resistance between the X and Y terminal in case of delta connection is, so this RB plus RC and RA both are in parallel. So that's why what is the equation? Then let us consider this is the series combination. This is the parallel resistance. So here RA into the combination of RB plus RC by RA plus RB plus RC. Okay, so because these two are parallel, okay, and these two are in series, and this series combination is in parallel with RA. So that's why, as we know, because let us consider this is the parallel resistance and this is the series combination resistance. Then if these two are in parallel, then RP into RS by RP plus RS. So in place of RS, what you have to substitute? RS is equal to RB plus RC. So that's why in place of RS, RB plus RC, and in place of RB, RA. So that's why then RA into RB plus RC by RA plus RB plus RC. Okay. Similarly, let us consider other the next two terminals. Okay. So these two terminals are, let us consider Y and Z. So in between Y and Z, what are the two resistors? R1 and R3 is there. So R1, R3 are connected in series, because when you are considering X and Y, then these Y terminals should be neglected. So that's why this resistance we should not consider. So that's why then we can say R1 and R2 are in R1 and R3 are in series. So that's why in between X and Z, so R1 plus R3. And similarly in between Y and Z, So in between Y and Z, what are the two resistors? R2 and R3. So these R1 should neglect, then R2 plus R3. A similar way, in the delta connection also, okay, so when you consider Y and Z terminals, which means here this is Y and this is Z terminals, in this case RA plus RB, so which means here RS is equal to RA plus RB, and here RP is equal to RC. If you substitute these RS RP values in this equation, then you will get in between Y and Z, so RC into RA plus RB by RA plus RB plus RC. In a similar way, in between X and Z also, in X and Z, these RA and RC are in series and this combination is in parallel with RB, so that at X and Y, the equivalent resistance between the X and Y terminals is RB into RA plus RC by RA plus RB plus RC. Okay, so then the next step is, just we have calculated the equivalent resistance between the various terminals in the star network as well as in the delta network. Okay, so now here in the star network, X and Y terminals, and in the delta network also X and Y terminals. Okay, so because in the star and delta we are transforming star to delta, so that's why just equate these R1 plus R2, which is equal to RA, because let us consider here X and Y equal to and X and Y equal to. So the left hand side terms are equal, then we can equate the right hand side terms, which means R1 plus R2 is equal to RA into RB plus RC by RA plus RB plus RC. Then that's what here I have just written. Let us consider, and similarly in the second equation also R2 plus R3, because these are in between Y and Z and here also Y and Z, then R2 plus R3, which is equal to RC into RA plus RB by RA plus RB plus RC. A similar way in between X and Z also, here also X and Z. So that's why just equate R1 plus R3 is equal to RB into RA plus RC by RA plus RB plus RC. So let us consider this is equation number 1 and this is equation number 2 and this is equation number 3. Actually, why we are doing these things? Finally, what we have to find? We have to find what is the value of RA, RB, RC in terms of R1, R2 and R3. Okay, so then let us just do 1 minus 2, equation 1 minus equation 2. Okay, so which means the left hand side is R1 plus R2 and right hand side is another equation. And even though in the equation 2 also left hand side R2 plus R3 and right hand side another equation. So just to subtract the left hand side terms and the right hand side terms, then the equation will become R1 plus R2 minus of R2 minus R2 plus R3 equal to this equation. This is RA into RB plus RC by RA plus RB plus RC minus RC into RA plus RB by RA plus RB plus RC. Then simplify this equation. Okay, because here as you can see this plus R2 and minus R2 gets cancelled. Then you will get R1 and minus of plus minus, then R1 minus R3. So R1 minus R3, and then here RA into RB and RA into RC, RA into RB plus RA into RC minus, okay, because in the here the denominator is same. Okay, you just take the common RA plus RB plus RC, then minus RC into RA minus RC into RB. So here also as you can see these RA RC and RA RC plus RA RC minus RA RC get cancelled. Then finally you will get R1 minus R3 is equal to RA RB minus RC RB by RA plus RB plus RC. Okay, so which means this is R1 minus R3 is equal to. Let us consider this is equation number 4. Let us consider this is equation number 4. So what we have done? Initially we have calculated the equivalent resistance between the two terminals in the star network as well as in the delta network. Okay, then we are equate the right hand side terms of the star network and as well as the delta network. Then you will get the equation number 1, 2, 3, and after that we have done the subtraction between the equation 1 and 2. So 1 minus 2. Then we have simplified. Then we will get if equation number 1 minus 2, which is equal to R1 minus R3 is equal to RA RB minus RC RB by RA plus RB plus RC. Then again let us consider equation number 3 and 4. Okay, equation number 3 and 4. So if you just add 3 and 4, okay, why we are doing 3 and 4 means here if you add these two, here plus R3 minus R3 gets cancelled, then you will get finally only the R1, the value of the R1. So then here R1 plus R3 the left hand side, and here R1 minus R3 plus R1 minus R3, and the right hand side terms E. Okay, then if you simplify this, again here these R3 gets cancelled, then R1 plus R1 is equal to 2R1, and here also as you can see this what is that, here RA, RB and RA, RB is there, but here plus RB, RC and minus RB, RC gets cancelled, then you will get RA, RB plus RA, RB, which is equal to 2 RA, RB by RA plus RB plus RC. Okay, then from this equation, these two gets cancelled, then R1 is equal to RA, RB by RA plus RB plus RC. The similar way, okay, if you want to find R2, then you can find R2 also in a similar way, then R2 is equal to RA, RC by RA plus RB plus RC, then R3 is equal to RB, RC by RA plus RB plus RC. Which means here it is not what is that, star to delta, it is delta to star. Both way we can transform. Okay, I mean in the next we will see how, because which means here we know the values of RA, RB and RC. Okay, then we are finding the R1 and R2, R3 values by using the values of RA, RB and RC. So which means here R1, okay, as you can see here R1 is connected to the terminal X or node X. So what are the other two resistors which are connected to this particular node X other than R1? RA and RB. So that's why you can see RA, RB by the total resistance RA plus RB plus RC. Then similarly R2, where is R2? Here R2 is connected to the terminal Y. What are the other two resistors which are connected to terminal Y from the delta network, which are RA and RC? So here RA and RC, which means here RA, RC by RA plus RB plus RC. And similar way, R3 is connected to the terminal Z. Okay, the other two resistors from the delta network which are connected to the terminal Z are RB and RC. So here RB plus RC by RA plus RB plus RC. So it is very easy to remember these equations. Okay, the star to delta or delta to star equations. Okay, so I hope everybody understood. Okay, I mean how we can transform, okay, star to delta and delta to star. Of course, here this is because we know the values of RA, RB, RC, which means initially this network is in the delta form. Then we are transforming this delta into the star form. Okay, this is not just delta to star. Here it is star. Yeah, delta to star, of course, because delta is there and star. Now we are converting star. Okay, delta to star. Okay, so then now let us find star to delta, because now the values of R1, R2, R3 we have calculated in terms of RA, RB and RC. Now we are going to discuss how the RA, RB, RC values in terms of R1, R2, R3. Okay, because vice versa, star to delta and delta to star. Then further here, let us, because R1, R2, okay, equation R1 into R2 and as well as R2 into R3 and as well as R1 into R3. Okay, so let us perform these, actions. Okay, so let us consider the equation. Okay, if you get the equation by subtracting R1 and R2, then let us consider that is equation number 5. Okay, so here if you do R1 and R2, of course here R1 is RA into RB by RA plus RB plus RC, and R2 is RA RC by RA plus RB plus RC. So RA RB into RA RC by RA plus RB plus RC whole square. Similarly, this is equation number 5, because R1 into RT we have considered, this is equation number 5. Then R2 into R3. Okay, similarly, let us consider this is equation number 6, and similarly R1 into R3, let us consider this is equation number 7. Okay, then add equation 5, 6, 7. Okay, this is 5, equation number 5, 6, 7. Okay, then you will get R1, R2 plus R2 R3 plus R1 R3 equals to, okay, these right hand side terms, okay, this one plus this one plus this one. Then simplify this equation, the same equation I have just written, okay. Then here you just multiply, okay, and simplify this equation. Then you will get finally, okay, after simplification, this R1 R2 plus R2 R3 plus R1 R3 is equal to RA RB RC into RA plus RB plus RC by RA plus RB plus RC whole square. Okay, so here one RA plus RB plus RC is there, and here the square is there, gets cancelled. Then finally you will get RA RB RC by RA plus RB plus RC, which is equal to R1 R2 plus R2 R3 plus R1 R3. Okay, then we know already what is R1. Okay, from equation number, from the previous slide, we know what is R1 is equal to RA RB by RA plus RB plus RC. Okay, then here RA and RB, okay, by RA plus RB plus RC. So this part we can replace with R1. Okay, this part we can replace with R1. So that's why then the left hand side terms are same, R1 R2 plus R2 R3 plus R1 R3 equals to this R1 plus RC. Okay, here in term, this term is replaced by R1 and RC is as it is, right? Then from this, if you send this R1 to the left hand side, then RC is equal to R1 R2 plus R2 R3 plus R1 R3 by R1. Okay, so which means here RC, where is RC here? This is RC. This RC is equal to, okay, R1 R2 R2 R3 plus R1 R3, because all other combinations, because R1 R2 R1 R3 and R2 R3 by R1, the opposite resistor which is connected to RC, okay, which means the other node, okay, the resistor which is connected to other node. Similarly, in this way, let us write this is RC now, so let us write RA value, okay. So which means here again the numerator is same, R1 R2 plus R2 R3 plus R1 R3 by, in the denominator, when we are finding RC in the denominator, it was R1. So now we are going to find RA. The opposite resistor is R3. So that's why here it is R3. In a similar way, suppose if you want to find RB is equal to, again numerator is same, R1 R2 plus R2 R3 plus R1 R3 by, what is the opposite resistor which is connected to RB? That is R2. So this is the delta to star. Sorry, star to delta, because we are having, we know the star equation, the star connected resistance value, and we have calculated the delta connected resistance values in terms of star connected network resistance values. Okay, so this is how we can transform the star to delta and delta to star. Okay, so here you can see this is RC, you can see RC, okay, the opposite resistor is R1, okay, and here RA, the numerator is same and the opposite resistor is R3. For RA, this is R3, and similarly for RB, the opposite resistor is R2, so that's why in the denominator R2. So which means this is star to delta. In star to delta, the numerator is same but the denominator is different. But in delta to star, the denominator is same but the numerator is different. Okay, just remember these points. Okay, so now you can see here, this is delta to star and this is star to delta. You can see in the delta to star here, the denominators are same, RA plus RB plus RC, RA plus RB plus RC. And in delta to star, the numerators are same, R1, R2 plus R2, R3 plus R1, R3. And here also R1, R2 plus R2, R3 plus R1, R3. And here also R1, R2 plus R2, R3 plus R1, R3 by R2. Okay, so this is the way to transform star to delta and delta to star transformation. So you have to remember these equations to apply star to delta and delta to star transformation. Then now we will take one example, okay, exactly where we need to apply these star to delta and delta to star transformations, right? So for that, here let us consider a network, and here we have to find the equivalent resistance between the terminals A and B. Okay, so usually if you want to find the equivalent resistance between any two terminals, okay, so first we will check with whether any two resistor combinations are in series or parallel, so that we are try to replace those two resistors with the equivalent resistance. Now we will check. Okay, so let us consider here these 10 ohms and 20 ohms. Okay, so whether these 10 and 20 are connected in series or parallel. Okay, first check with the series. So of course these 10 and 20 is having one common node. Okay, but this common node is shared with this 10 ohms resistor. So which means these two are not in series. And parallel, because it is having only one common node, so that's why these two are not even parallel. So which means we cannot define these 10 ohms and 20 ohms are series or parallel. Then we will check with again this 20 and this 10. The same problem here also. Of course one common node, but this common node is connected to again this 10 ohms resistor. So we cannot define this also. Then let us take these 10 and this 20. Again here also one common node, but this common node is connected to this 10 ohms. So we cannot define these two also. These two combinations also. And let us take with this 10 ohms and this 10 ohms. Again here also one common node, but this common node is connected to another resistor. So this combination is also not possible. And let us consider this 10 ohms and this 10 ohms. Okay. But again here one common node, but this common node is connected to 20 ampere. The 20 ohms. So even though we cannot define these two combinations also. So which means here there is no possibility to identify the combination of any two resistors are in series or parallel. Then how to reduce this network? Then how to find the equivalent resistance between the terminals A and B? So in this particular situation, we need to apply the star to delta or delta to star transformation. Then here first we need to identify, okay, whether any delta connection is there, okay, or any star connection is there, okay, which star connection we need to transform into delta connection, or which delta connection we need to transform into star connection, that we need to identify. Okay, so here let us identify this is simply, okay, we can know this is a delta connection, and this delta connection we can transform into star connection, right? So if you convert this into star connection, then you will get like this. Okay, because this delta resistor, okay, because here this way, right? Okay, so which means here like this. So now you can easily now check, okay, whether any two possibilities are there to, identify series or parallel. Yes, of course, these 20 ohms and this resistor are in series. So we can replace this as a one resistor. And again, these 20 ohms and these are in series because only one common node, and that common node is not shared with any other element. And again here this one also. Okay, so which means we are transforming delta to star connection, okay, to get or to simplify or to reduce the network, to identify, okay, or to calculate the equivalent resistance between any two other resistances. Okay, fine. Now we are just converting the delta to star connection. Now we need to find the value of this resistor and this resistor and this resistor. Just now we have discussed the equations for this. Okay, so here, of course, this is the star network that we are having, delta network, and we are going to convert this delta network into the star network. Okay, and now we are going to find the values of these. Okay, so which means here R1, because here RA, RB, RC, let us consider. Okay, and let us consider R1, R2, R3 resistors. Then R1 is equal to RB, RC by RA plus RB plus RC. Even you no need to remember what is R1 and what is RA, RB. Okay, you just to draw here like this. Okay, we know these values. Okay, but we don't know these values. Let us consider this is R1, R2 and R3. Okay, so if you want to find R1, okay, which means this R1, okay, what are the other two resistors which is connected to this node? 10 and 10. Okay, so which means 10 into 10 by 10 plus 10 plus 10. Okay, because all the values are 10, so no need to worry, because in all the cases again 10 into 10 by 10 plus 10. Okay, then you will get the same values because all the resistor values are equal, 10, 10, 10. So if you want to find R3, what are the two other resistors connected to this particular node? 10 and 10. So that's why 10 into 10 by again the total resistance. So like this we can find the values of R1, R2 and R3. Okay. So then R1, R2, R3. Okay. Because here RA equal to RB equal to RC equal to 10 ohms. So that's why then R1 equal to R2 equal to R3 is equal to also you will get 3.3 ohms. Then you can here R1 is equal to 3.3 ohms, and here R2 is equal to also 3.3 ohms, and R3 is equal to also 3.3 ohms. Okay. So now this is after converting the delta to star, this is our network. Then now these 3.3 and 20 ohms, these 3.3 and 20 ohms are connected in series, and again here these 3.3 20 ohms are connected in series, and these 3.3 and these 20 ohms are connected in series. Then we can replace this with 23.3, and this also we can replace with 23.3 ohms resistor, and this also we can replace with 23.3 ohms resistor, because these two are in series. Okay. So as you can see here, now this is transformed into like this. Okay. So R equivalent is equal to R1 plus R2 plus R3. So 22, because of course, yes, sorry, I forgot to tell you here. We cannot transform this one because we need to find the resistance between these two terminals. So we should not disturb these two terminals. So that's why we should not, of course these two are in series, but we need to find the equivalent resistance between A and B terminals. So that's why we should not disturb these A and B terminals. So that's why we are not replacing these two resistors with the equivalent resistors. Okay, so we are considering only these two, right? Yeah. So then this is we have transformed into 23.3 and 23.3. Okay. Now again check. Again. Okay. And this resistor, of course, having one common node, but this common node is connected to 10 ohms, so we cannot define. And even similar way, these two combinations also we cannot define because one common node and connected to 10. Okay. So now what we want to do is, again, this is the, after reducing the network, this is our final network. Then again you can see this is one more delta connection. And now again we are transforming this delta connection into the star connection. Okay. And then again we are finding the same by using the same equations. Okay. We are finding these R1, R2 and R3. Okay. So then R1, R2, R3 values are, this is not RA, RB, of course RA value is, let us consider 22, and RB is 22, and RC is 10 ohms. Okay. Then here the R1, R2, R3 values, okay, we know already equations. So directly we can substitute in these equations RA, RB, RC values. Then you will get R1, R2, R3 values. Okay. Then here, this is the network. Now it is, now you can see here, of course, this B terminal, we are not disturbing, but these two are in series. Okay. So you can just replace with the series connection. Okay. Right. These two are in series. Okay. So this is combination. And again, these two are also in series and these two are also in series, right? So you can replace all these resistances, right? So here 10 plus 4.12 is 14.12, and 10 plus 4.12 is 14.12, and here 9 plus 3.33 is 9.61 plus 3.33 is 12.94 ohms. Sorry, not amperes. Okay. 14.12 ohms and 12.94 ohms and 14.12 ohms. Okay. Now, this is our final network that after applying the delta to star transformation. Okay. Now, let us identify. Okay. So, here, these three. Okay. How these three are connected? I mean, which means these two resistors. Okay. So here again, as you can see, okay, these two resistors having two common nodes, because 1 and 2, right? Because here 14.12 is connected in between A and B, and 14.12 is also connected in between, sorry, let us consider this is C, A and C. So if you simplify these and in place in between A and C, so this is that resistance, because again this 20 and 12.4 is as it is. And here, just replace that resistance value, because R1, R2 by R1 plus R2, because these two are in parallel. So then, here the equivalent resistance is 7.06. And again, you can see these 12.94 and 7.06 are in series, because these two are having only one common node. Of course, these two represent the same node. Okay, then, which is 12 plus 7. Okay, so which is, as you can see, R equivalent is equal to R1 plus R2. So which is almost around 20 ohms. Then now the 20 ohms and 20 ohms are in parallel, because again these two resistors are connected in between the two nodes A and B, because these two represents the same node, right? Then here R equivalent is equal to 10 ohms. So this is how we can find the equivalent resistance between any two terminals. Okay. So by using this star to delta and delta to transformation. Of course, if you are able to identify, okay, because as you can see here, okay, so by taking this and this resistance, because three resistors are connecting at one common node, of course this is in the star what is that connection, but okay, if you are able to identify the combination of any two resistors are in series and parallel, then we will go for the series and parallel combination only. But if you are not able to identify, okay, any combination of the resistors are in series and parallel, then we will go for the star to delta and delta to star transformation. Okay, right. So this is how we can apply the delta to star and star transformation to find the equivalent resistance between any two terminals. Thank you. In next class, we will discuss the remaining topics.
Like, share and subscribe. Hit the bell icon for more updates.